So one of the things we'd like to do is to push ahead a bit to cover some more of the essential material, the basics about logic and computer architecture. So the foundation of logic and computer architecture is to work with only two values. And it's counterintuitive to think of a zero as a non-value. But in the binary system, base two number system, I just want to make some quick notes here and make these really large so everybody can see them. So when we talk about logic gates, we are talking about the hardware equivalents of Boolean operators. Okay. When we talk about Boolean operators, we're talking about are the software equivalent. We're going to be working both with hardware and with software, okay? And that's a really important distinction. That's something that we want everyone to understand implicitly. I'm going to change the layout so it's wide. Yeah, there we go. Everybody with me?
Yeah.
Yeah.
Yeah. I think what I'll do is just to make this the same. Right? So Elijah's in the mix now. Good morning, Elijah. How are you?
Good morning.
Good morning. Okay. So some quick definitions here, and this is something that, well, we want you to show good form. So as a part of our orientation about basic computer architecture and the Boolean logic that forms the basis of everything, right? We're going to be referring to things called logic gates. And logic gates are the hardware equivalents of Boolean operators. Generically, we could call these digital components on a very basic level. Think of them as the cells in a tissue, and the tissues as a part of an organ, and an organ is a part of an organ system. So they're building blocks, okay? And Boolean operators, when we refer to Boolean operators, when you hear the word Boolean and operators, we're talking about software equivalents. So these are things we can do with a simulator. These are things we can do with a programming language. It's not in hardware, but there's basic logic, you know. And then the word function is very specific, right? So when we talk about function, we're talking about combinations of operators. And I'm going to talk about that in just a second. Essentially, in binary, right, there are only two values. Now, logic has a number of different contexts. So technically speaking, I guess we could, if we were talking in pure terms, when you have something in quotes, it kind of indicates that something may not be something, right? So the issue with binary or base 2, right? So when we talk about binary system, we're talking about base 2 number system. And this is something you'll get into quite a bit with your number theory and then with your discrete mathematics course. There are only 2 values, and that's 1 and 0. Now, there's great mathematical debate, depending on your perspective, and some math faculty would say, oh, that's an exaggeration. But for a time, 0 represents a non-value. It's a non-quantity. So in a sense, it can be kind of confusing to refer to it as a value. But remember that the binary world works with on and off, and 0 represents off. Or 0 represents O for open. O for off or O for open, as in open circuit. The circuit is broken. Okay? This is from last week. I don't want to get into a debate about whether or not 0 actually represents a discrete value as opposed to a non-value on a number line, right? So when you're looking in terms of math theory and you look at a number line, 0 is unique because it represents the absence of a discrete value or a specific value. It's a non-value. But in the binary world, it's special. In the world of computer architecture, 0 has huge implications, in part because it helps you keep space or perspective about where something is. So here's, which would you prefer to be paid? All right. Everybody understands implicitly and intuitively that 0 helps you keep which place a number value is. So, and we understand in the decimal system that this is the ones place. And in the decimal system, the next place over, a two-digit number, the second digit represents 10, right? And in the base 10 number system or decimal system, the third digit of a 3-digit number represents the hundreds. So everybody instinctively knows that if I'm talking about something like the number 372, right? So if I'm talking about the number 372, three by 100, okay? So this is the 300s place. And if I have a 3 here, I know that I am really talking about 3 100 quantities, 3 times 100 quantities, or 300, right? In the tens, I'm dealing with 7 tens or 70, right? So everybody understands this instinctively because we grew up with it. More to the point, we're decimal animals. When you think about our biology, how many fingers and toes do we have normally?
10.
10, right? So it's just intuitive and it's what we grow up with. Now, one of the hardest things to do in a new discipline is to unlearn some things. Like the fact that this is very important and represents something called null, right? Null means there's nothing in there. There's no value, right? And the fact that 0 represents a non-value ordinarily would be interpreted differently based on the different number systems, depending on, well, it would mean there's a non-value in a given place for so many digits of a number, right? The point I'm trying to make is that everybody seems to think that 0 is unimportant. But in the world of binary, you'd have to change your way of thinking. And that's part of the mental wrinkle that holds people back where they need to understand some absolutes about the digital universe, okay? So I just wanted you to be aware, if you ever hear the term logic gates, that's hardware. If we're talking about Boolean operators, we're talking about software. If we're talking about Boolean functions, we're talking about combinations of operators, and the values of a binary file or system are expressed in ones and zeros. So binary characters, binary alphanumeric characters, binary numbers are expressed in ones and zeros. And this just takes a lot of getting used to, right? I'm going to say 7 times 10, 2 times 1. Everybody gets what we're saying here, right? Any questions about what we've covered so far?
No.
No.
So when you're talking about the essential logical operators, there are 3. And, or, and not. Now, here's the weird part. This is where you have to unlearn some things. In the binary world, in Boolean logic, when you use this Boolean operator, you're multiplying. Or is equal to addition.
Oh, it's ringing at 10:25.
Done. 5 minutes until it rings.
It's the reverse of the stated value. So what am I saying? When you have 1 and 1, you're multiplying 1 times 1. Or put another way, if I have the Boolean number 1, 0, which represents the decimal number 2, and I multiply it, I'm using and if I use 1, 1, okay, this equals, so let's break this down. This is the ones place, this is the twos place. And unlike decimals where you have ones place, tens place, hundreds place, thousands place, in binary values, this is the ones place, the twos place, the fours place, the eights place, the 16s place, the 32s place, the 64s place, and the 128 place. Now that's kind of odd, but what I want you to catch is 1, 2, 4, 8. Does anyone notice a pattern there? 1, 2, 4, 8, 16. What's happening as I move left?
Count them by twos.
Multiples of 2.
We're doubling twos. Yeah, we're doubling the quantity, right? And if there's a 0 here, that means I don't have any ones, I don't have any twos, I don't have any
Not there
fours,
yet?
but I have an 8. So this is equal.
Yeah, he's becoming a little late.
I have an 8, I have a 16, I have a 32, and I have a 120.
Oh, yeah. So you know the drill. Do your stretches.
Can I get you to mute your microphone, please? Whoever it is that's
And do a 10-minute walks on the treadmill
session, please.
to loosen up the leg muscle.
Okay, I'll mute you if you won't. Joshua? Okay. All right. So if I have a 1 in the 128th place, in
You
the
just said something, Dr. Cantor?
Your microphone was active and there was some background noise. Maybe by the time I looked at the listing in front of me, it had changed, right? So that wasn't you, but I was just asking someone to mute their microphone because we were picking up on another conversation and it was stepping on the recording. So,
Oh, okay.
okay, so just like the decimal number 372 equals 3 100s plus 7 tens plus 2 1s, this binary number equals a 128. There is no value in the 64s column, but there is a value in the 32s column. So it's 128 plus 32 plus 16, which is here, plus 8, and then the rest are zeros. I have a 0, 4. There are 0 4s, 0 2s, and 0 1s. So what is this number in decimal? Well, this is 160, right? And then that's 176 and that's 184, I think, right? Is that correct? Now, how would you cheat? What's the easy button for this when you're working with binary universe, right? You can go to your calculator and you can convert your calculator in Windows into a programmer calculator, which makes life really interesting because if you select binary instead of decimal, you can actually punch in that number. So I'm going to punch in this portion of the 8-bit number, which is called a byte, and each 4-bit portion is actually called a nibble or a D word. So a byte and a nibble. I think somebody had a sense of humor, right? So this whole thing, 8 bits, is considered a byte in binary terms, B-Y-T-E, byte. And each half of the byte, 4 bits, is referred to as a nibble or D word, okay? So I'm going to plug this in, and as I plug in this binary number, you're going to see up here that the decimal equivalent is going to kick in, okay? So 10111000. Can everybody see what I just did there?
Yes.
And what I get for a total is 184, and as a decimal number, that's what this binary value represents. The integer in decimal of 184 as a whole number. Now, there aren't any decimal points. We're not dealing with real numbers where there's partial fractions of a number. We'll get to that later, okay? But for now, let's just deal with whole numbers. The important thing is we want you to think in different terms, and this one in particular is something that catches people all the time. When they see this in a binary equation, people assume that we're summing 10 and 11. We're not adding 10 and 11. Ordinarily in words, verbally, we'd say, if I have 10 and 11, that equals 21 in decimal, right? But 10 and 11, and this is the part that kills people, it's like, okay, equals what? Well, I have no ones, I have a 2. So in decimal terms, this is a 2. In decimal terms, I have a 2 plus a 1, so this is 3. So 2 and 3 in binary operator, we're using binary operators. The and is actually a mathematical multiplication. So what we're doing here is 2 multiplied by 3. What is this?
6.
6 is correct, thank you, in decimal. So what is that in binary? Well, 110 is 6. I don't have a 1. I have a 2 and I have a 4. What's 2 plus 4?
6.
6, right? In binary. And so this is kind of, it's a process. It takes time. You have to be patient with yourself. But there's one more thing that I find very awkward. When you represent and as a multiplier, you use a large dot. And in other mathematical circles, that represents multiplication. That's not the problem. That's not the problem. The problem is that when you use a symbol to represent or in binary operations, you're using the plus sign. And then as soon as people see the plus sign, they go, oh. And that's where that wrinkle in your brain goes, and is always summing things, right? So what happens is that we'll show you an equation of 2 values. And let's look at your study guide, right? So your study guide has an example of this. So we talk about this quite a bit, and we talk about base 16 in the study guide, right? And here we're taking decimal equivalents of a binary values or a hexadecimal value. We'll get into bit shift calculations in a minute. I'm looking for the logical operator. I don't see it. Okay. So every now and then we'll have a module study guide addendum. Is everybody with me?
Yes.
An addendum.
Yes. And
The addendum is going to have stuff like this in there, right? Where it's extra information. And we're going to start using that. You insert the dot symbol to represent and. So if I'm inserting a symbol that represents and, Boolean, I'm inserting a symbol. And if I look at more symbols, I'm looking for the dot, right? So this is kind of a pain in the neck to find, but I'm showing you how to do it in case you're submitting information. And I actually have a template. I'm going to post a template that has these Boolean symbols, and it should not be quite so hard to find this goofy thing. Maybe the font we need to change. So I'm going to change to like Arial or symbol. There's actually a symbol font. There we go. Yeah, now we'll get to it quick. There it is, right there. Everybody see this? Insert. Now that is and, which is also multiplication, mathematically speaking. The plus sign. Okay. Here's the point. Your brain does a flip, or at least a lot of students, their brain does a flip. And when we have an equation where we're using binary values and we're using this or this, right? People see this and they and it, and if their mind isn't completely clear about that, people see and, they see a value, we're gonna combine 6 and 27. They hear and they do this. And when we're combining 6 and 27 in Boolean terms, we're actually multiplying. So we're not adding, even though you hear verbally the word and. Is this clear? Am I explaining this?
Yes.
Yes.
Yeah, it's one of the stumbling blocks. It's a needless stumbling block, and you're not going to find most textbooks address this. They just don't. But in terms of learning psychology, right? So the psychology of learning, we've actually studied this in the classroom, and we found that this is one of the stumbling blocks when it comes to computer science, especially for computer architecture, is that there's this verbal understanding of what and means in the decimal number system that we grew up with. And in verbal terms, it means plus when you're anding things. But and actually means multiplication. So we're multiplying instead of adding. There's one more thing that we need to understand about and, or, and not, and that's how they function. So when you use and on Boolean, here's what it means. And means if all inputs are true or 1 or yes, then the output or result is true or 1 or yes. But if any input is 0 or no or false, then the output is false or 0 or no. So I want to show this to you, okay? And we're going to come up with a string of operations here, okay? Everybody with me?
Yeah.
Okay, first of all, are we dealing with and or when you see this?
And
And is that multiplication or addition?
Multiplication.
multiplication.
Okay, and in terms of the logic and how this works, it means that if all inputs are true or 1 or yes, then the output is equal to 1 or true or yes. But if any of the inputs are 0, no, or false, then the output is what? 0 or no or false. Okay, so what is this?
0, no, or false.
It is 0 or no or false. Thank you so much. Now, I did not have the screen up at that time, but may I ask who provided that answer?
Hey, Michaela.
Michaela. Okay. Thank you for taking a mild risk and jumping out there. And I mean, it could be very simple if you're following along, and if you're not, then yeah. All right. So how is it that we get a true? Well, the only way you're going to get a true is if you do this, right? Let's copy. Oh, I'm sorry. Ooh. We're going to copy this, and then we're going to paste this, and I'm going to turn this into a 1. Now, what is the answer here?
1 or yes or true.
1 or a yes or a true is correct. Okay. Now, or works differently. So or means if any input is 1 or true or yes, then the output equals 1. Otherwise, output equals false. So you're gonna start to notice that I start to flip in like I start to shorten my descriptions, right? I'm starting to write more like pseudocode, okay? Or means if any input is 1 or true or yes, any of them, then the output is equal to 1. So in this string, if you just have 1, right? So what are we saying? Well, let's take this as an example. Okay, same example. Only instead of this, we're going to put a plus sign, right? Everybody with me?
Yes.
Yes.
So what do we have here?
I
1
think it's
or
1,
true or
maybe.
yes.
Say again. Our
1
output,
or true or yes.
1 or 2 or yes is correct. Yeah. Thank you, both of you. Okay, what about this? Let's make it harder. And you're gonna go, yeah, but this is like a joke, right? Well, just bear with me here, okay? And how do you read this? When you're reading this verbally, you're gonna say 0 and, oh no, I didn't. You see what I just did there?
Yeah, you called it and instead of
Yeah,
or.
and it's the or.
Yeah, it just happens, right? And then you get into a different mindset and you're like, oh, why can't I get 0 or 0 or 0 or 1 equals what?
1.
1 or 2 or yes. Now there's an easy button for and or. If all the values are true, the output is true for an and. If all the values are false, the output for or is false. All in, all ones, and is 1. Well, so is or, right? But in what case does or, see, all of the inputs have to be 1 in order for this to be 1. And that's the only case. Every other case is 0, every single other case. In here, all the outputs are 1, because if at least one of them is true, then like here, then the output is true. But there's one case where or is false, only one case. All the inputs are false, okay? So let's do the shortcut. Let's get an understanding of the shortcut understanding here. If all inputs 1, then output equals 1. That's huge. Now, if all inputs 0, then output equals 0 when or is the operator. Now, let's talk about not for a minute. I call this the Boolean wildcard. You can sprinkle a few knots in there and it's like sprinkling salsa or cayenne pepper in the middle of a dish that you cook for someone, right? When you mix it up, not means the reverse equivalent. So here's an example of not one. The input is always reversed. So if the input is a 1, what's not 1? In Boolean terms. There's
Zero.
only, yeah, 0. There's only one other choice. I mean, that's what's nice about binary, isn't it? If it's not 1, then the only other chance, the only other thing it could be is 0. Well, what if it's not 0?
It's 1.
It's equal to 1, right? So what are we saying? You take whatever value is inputted, and there's only one input. Now, that's the difference between and or. This is another huge difference. You can have multiple inputs for and or. You can only have one value, only one, for an input with not. And not flips it, okay? Not's a flipper. Any questions about what we've covered so far with Boolean logic?
Is there a symbol for not?
That's a great question. And I believe the symbol for not is an exclamation point, but I'm gonna qualify that statement, okay? So, whoops. If you go like this, that equals not. That's
Kind of
one,
like Java.
yeah, that's one common representation for not. There are others, and it depends on the programming language, but in terms of pure Boolean logic, it's the exclamation point, okay? The other thing too is that if you have a value that has a line over it, and we're going to talk about this quite a bit. If you have a variable and the variable has a line drawn over it, that's called a bar. So you can have the value of x, for example. And if x has a line over it, we call that x bar. That means whatever x is, it's knotted. So the bar represents, so the exclamation point generically and the bar. Let me see if I can find a quick, let's see. Template, symbols. So the pipe symbol on your keyboard, the pipe symbol looks like two lines over each other, and there's a little opening there, which is supposed to represent like the opening of a pipe, right? The inside of a pipe. That's the pipe symbol. That represents or in many programming languages. And is represented with an ampersand. Does everybody know what an ampersand is?
Yeah.
Okay, this,
No.
it's that thing.
Oh, it's called an ampersand. I always
Yeah.
said I just see it as the and symbol.
And the pipe, when I do the pipe, it's the shift backslash, it's the shift backslash key. And the problem is that it looks like an elongated I, right? That's equal to or. So not and an or. I wanted to talk just for a brief moment, very quickly, about NAND to Tetris, right? So in your solution I'm about to post, I'm going to post a link nantotetris.org. go to the software. What you have to do, there's going to be a short video. It's called Project Zero. Project Zero gets you started. It shows you how to install the software. It walks you through this screen. It shows you what to do to install the Java Runtime Edition. If you don't have Java Runtime Edition installed, you can click this link and it'll take you separately to the Java Runtime Edition website where you can download the JRE that you need to operate your simulation environment. Now, your simulation environment, all you're doing is getting the software set up. The best way to do this when you download it, it's going to be a zip file, and you're going to want to take that zip file and open it up and copy the contents. Right? You're going to want to copy the contents, which is a tools folder and a projects folder, and you're going to want to put it in a directory with the same name. You'll see in the video. So there will be a video, and I'm going to post your 1.4 assignment, right? So we have 1.3 out there, but before the day is out, we're going to post 1.4, the solution, okay? Any question, and it's due by this Saturday, 11:59 p.m. Any questions before we clear our session today? Okay, going once.